Hello, so I'm going to talk about the average case hardness for ACC0 circuits. So first, let's see some oversimplified history on this problem. So people wanted to prove circuit lower bounds and show P is not equal to NP, but that is hard. But it's not the case back in 1980s. At least that's what not people thought at that time. The question at that time is to understand the constant depth circuits first. So at AC0 to be the constant depth and or not circuits. And people first show a strong lower bound for AC0. So the hard function at that time is just parity, and the parity is the function that outputs 1 if the number of 1 is even. And so okay, now we know parity is hard for AC0, and let's make AC0 stronger. What about just adding parity gates to AC0? And then the philosophy there is to strengthen the circuit class just a little bit by adding the most single function it cannot compute at available gates. So hopefully you can get to general circuits very soon. So let's define AC0P to be the AC0 circuits extended with the mod P gates. And mod P means that the function outputs 1 if the number of 1 can be divided by P. And Radbarov and Smolensky show strong lower bounds for AC0P for a prime P. And the hard function for AC02 is just mod 3. And or majority, but the mod 3 is simpler than that, so let's think about it first. So nice, everything so far was very successful. And we know mod 3 is hard for AC02 circuits, right? So let's make AC02 a little bit stronger. What about adding mod 3 gates to AC02? Shouldn't be that harder, right? So we have AC0, we add parity, and it becomes AC02, and then we add mod 3, and it becomes AC06. So having both mod 3 gates and mod 2 gates is equivalent to having mod 6 gates. So as you may already know, this circuit class, the so-called the ACC circuit class, is notoriously hard. And since then, things went downhill, and it seems very hard to put any non-trivial lower bounds against them. Indeed, it had been open for a long time that whether nexp, the non-deterministic exponential time, has polynomial size AC06 circuits of step 3. So, but I mean, this might come, right? And in 2011, R. Williams proved that NX does not have polynomial size AC0 circuits. So AC0 means the union of AC0M for all constants M. So now the M can also be a composite. This is a very cool result, both because of the theoretical importance as it crosses all the previous barriers in complexity, like relativization, algebraization, or natural proofs. Also, in terms of proof techniques, it combines many gems from classical complexity, like PCP theorem, IP equals P space, hardness versus randomness, and time hierarchy theorems. So let's take a closer look. This is a big breakthrough, but still it has some drawbacks compared to previous lower bounds. NX is a pretty gigantic class, and we want NP, right? Previous lower bounds are usually for easy functions in P, like parity or majority. And it only gives you worst case lower bounds. And the previous lower bounds also can be extended to average case setting. And the average case lower bounds may have more potential applications, like building PRGs. So So to deal with these drawbacks, people have been working on extending this lower bound. So in 2012, R. Williams proved that nx kept conexp with 1 bit of advice. So this is the exponential time version of the more famous class NP capital NP that not have polynomial size AC0 circuits. So in this way, we can have lower bound. We make nx a bit smaller. And later, Lijie Chen, Olivera, and Sutherland proved that nx cannot be half plus 1 over polylog approximated by polynomial size AC0 circuits. So this extends the lower bound to the average case. In 2000, very recently, Murray and R. Williams proved that NQP, the non-deterministic quasi-polynomial time, does not have polynomial size AC0 circuits. This makes nx much smaller. So in this work, we simultaneously improved on all the above results by proving that NQP cannot be half plus 1 over polylog approximated by polynomial size AC0 circuits. And the same holds for NQP capital NQP with 1 bit of advice. So this is the quasi-polynomial time version of the more famous class NP capital NP. So let's see why average case lower bounds are harder to prove, because I want to convince you this work is non-trivial. So let's see how previous lower bounds worked for the worst case lower bound. So this is essentially a proof by contradiction. You first assume NQP is in AC0 for the sake of contradiction. And then you apply the easy witness lemma, which says something like every NQP verifier has polynomial size AC0 circuits with AC0 witnesses. Then you use that and a non-trivial circuit analysis algorithm for AC0 to contradict non-deterministic time hierarchy. Then you get the contradiction. So the core here is the easy witness lemma. So I want to give a formal definition of that lemma. So first, let L to be a language in NQP, and V be a verifier for L. This means that X is in L if and only if there exists a proof Y such that VXY outputs 1. So this Y makes V accepts the input X. And the V takes polynomial time in the input length, which is X plus Y. And the Y has a quasi-polynomial size. So V is the verifier for L. And the easy witness lemma says that if NQP is in AC0, then all verifiers V for L have AC0 encodable witness. So what does this mean? This means that X is in L if and only if there exists a polynomial size AC0 circuit D such that the truth table of D makes V accepts the input X. So now you don't have to search over all possible witness Y. You only need to search for the truth table of polynomial size AC0 circuits, which is much smaller than the all possible quasi-polynomial length strings. So the next step is to combine the above with PCP. So we assume NQP is in AC0, and let B be a large enough constant, and L be n times 2 log n to the B. We fix the previous verifier for L to be a PCP verifier. Then, combining that with the easy witness lemma, we have the following. If X is in L, then there exists a polynomial size AC0 circuit C such that the PCP verifier will always accept this circuit as an oracle. So this is just the completeness of the PCP. Combining with the easy witness lemma. And if X is not in L, then just by the by the soundness of the PCP, for all possible oracle, this V on input X will reject O with high probability. So this is just combining the PCP with the easy witness lemma. As we assume NQP is in ACC0. So finally, we want to simulate this language L in some time smaller than 2 to log n to the B. Then we have the contradiction to the n-time hierarchy. So to do this, we just do the straightforward thing. First, we guess a polynomial size ACC0 circuit C. And then we use some algorithm to estimate the probability that V accepts C. And we accept if the probability or estimation is greater than 1/2. So this is the place where the algorithm comes to play. And this actually decides L. So if we can do the estimation faster than 2 to log n to the B, then our final algorithm will also be faster than 2 to log n to the B. So can we try to implement this plan for the average case? So first, we assume NQP can be, say, 0.9 approximated by ACC0 circuits. And then we apply the easy witness lemma again, maybe to show that NQP verifiers still have polynomial size ACC0 circuit witness. And we use that and a non-trivial algorithm to contradict n-time hierarchy. However, the problem, this becomes problematic because the second step. But now we can only assume that NQP can be 0.9, say, approximated by ACC0 circuits. Can we show an average case easy-witness lemmas as before? Something like if NQP can be approximated by ACC0 circuits, then NQP still has ACC succinct witnesses. The old proof doesn't work and just breaks because it crucially depends on the assumption is worst case. The assumption is NQP can be completely computed by ACC0 circuits. So let's see how the previous works circumvent, bypass this issue. So they try to work around this with a big weapon. They use worst case to average case hardness amplification, which is a big weapon, as you can see. So it's just start with a hard function L in nx per capital nx, which is worst case hard for ACC0. The idea is to compute an error correcting code of the entire truth table of L on some input length n. And then you make the code word to be the truth table of the new language L tilde on some new input lengths of O n. Then by arguing about the local decoder of the error correcting code, the L tilde will be average case hard for ACC0. But the issue is that computing the error correcting code of the entire truth table takes at least exponential time. Even if L is in NQP capital NQP, L tilde will not be in NQP anymore. So now you can see the difficulty. We need to prove an average case lower bound directly without going through either witness lemma, because we don't have them in the average case, or hardness amplification, because this requires at least exponential time, and we want to prove lower bound for n quasi-polynomial time. So we are going to use a more direct approach, which combines MA lower bounds and non-deterministic PRGs. I will define them and motivate them in the next slide. So first, what is an MA algorithm? MA algorithm is just NP with a randomized verifier. So now you are given an input X, and you guess some witness Y, some proof Y, and you toss some coins R. And the X is in L if there exists a proof such that A will accept with high probability. And if X is not in L, then for all proof, A will reject with high probability. And non-deterministic PRG is combine non-determinism with PRG. Given an input 1 to the n, it gets a witness W first, and either rejects W and just stop, or then it takes a seed and computes a PRG. So it may not compute a PRG on all branches, but at least some branches it computes a PRG. So we can apply NPRG to de-randomize MA to NP, just as follows. Given an input X, we guess both the proof Y and the W for the NPRG. If NPRG accepts W, then we use the NPRG to estimate the probability that A accepts the proof Y. And we accept only if the probability is greater than 1/2. So the running time actually depends on the seed length of the NPRG. So now let's see our new approach in a nutshell, which is greatly simplified. First, we prove an MA lower bound, MA average case lower bound against ACC0. That is, we find a hard language L in MA, which is average case hard for ACC0. Then we show that if NQP can be approximated by ACC0, then there is a non-deterministic PRG with polylog seed length. Now we can apply this NPRG to put the hard MA language L from the first item in NQP, because we can de-randomize that MA into NQP. So now NQP cannot be approximated by ACC0, which is a contradiction. So finally, I want to make some technical notes for more hardcore people and give other people a chance to take a nap. So the previous description is very simplified, and we actually, assuming NQP can be approximated by ACC0, we can only construct an PRG which works for only infinitely many input lengths, and can only de-randomize low depth circuits. Low depth means polylogon. So the short answer is that we don't have almost everywhere n-time hierarchy, and we also don't have p-complete random self-reducible languages. But we do have NC1 complete random self-reducible languages. That's why it works for polylogon depth circuits. With this infinitely often NPRG, we can only de-randomize MA on infinitely many input lengths. So we also want this MA language to be hard on almost all input lengths. But we don't know how to prove an almost everywhere MA lower bound. But we can prove an almost everywhere MA lower bound, which is still enough, following the key ideas of Murray-Williams 2018. We can indeed prove an MA average case lower bounds against polylogon depth circuits. And the MA language have polylogon depth computable predicate. The predicate here is just the function AXYR. Given input X, proof Y, and the randomness R. The function AXYR decides whether the answer accepts this Y given the randomness. So if the MA language have low depth predicate, it can be de-randomized by NPRG. Of course, check the paper for more details. So actually, we have a new work on this line. So recently, we can show that half plus one over polylogon is not enough for building a PRG. But recently, we can show something stronger. We can show NQP cannot be half plus 2 minus log n to the k approximated by ACC0 circuits for any constant k. So this is enough to give you some PRG. The new work crucially depends on PCP proximity and also crypto in NC0. Maybe this shows the unity of the complexity theory. So that's it. Thanks. Any questions?